Welcome to our talk. Today I will be talking about our work on interactive design and object-based visualization of arbitrary non-Euclidean kaleidoscopic Orbifolds. This is joint work with Jinta Zheng and Professor Zhang. Orbifolds are a modern mathematical concept that have found applications in string theory, low-dimensional topology, as well as tensor field topology, remeshing, and texture synthesis. In this paper, we propose a mirror-based visualization for Orbifolds, in which an Orbifold is visually represented as a room with mirrors. Through mirror reflections in three-dimensional spaces, the user can gain intuition into the concept and important properties of the underlying Orbifold. Most Orbifolds are non-Euclidean, such as the spherical and hyperbolic Orbifolds shown here. We provide an interactive design system for any kaleidoscopic Orbifolds, whether Euclidean, spherical, or hyperbolic. In addition, our design can be used to generate non-Orbifolds, such as the room shown here. Due to the improper configuration of the room, visual artifacts can result, such as the two-headed dragons. Our contributions include a mirror-based visual metaphor for Orbifolds, as well as an interactive design system. At the core of our system are algorithms to create arbitrary kaleidoscopic Orbifolds, to embed an object inside a non-Euclidean space, and to construct the universal cover of an Orbifold. In addition, we provide an adapted rendering algorithm enabling rays to follow geodesics in non-Euclidean spaces. Furthermore, we provide an enumeration of all two-dimensional kaleidoscopic Orbifolds. Our work belongs to math visualization, a field within visualization that has seen much research over the years. Orbifolds have been visualized using two-dimensional texture patterns. Orbifolds have also been used to describe degenerate points in tensor field topology, construct periodic global parameterizations of surfaces, as well as semi-regular remeshing. The definition of Orbifolds is rather convoluted, involving concepts such as topological spaces, charts, group actions, grouping maps, and group homomorphisms. Next, I will describe a number of concepts and properties of Orbifolds using our mirror-based metaphor. Starting with a square room with a Lucy statue inside, we can make the room look larger by placing a mirror on the wall. The virtual room is the reflection of the original room. Together, the original room and the virtual room form the universal cover of the original room, which is the Orbifold. When placing a second mirror on an adjacent wall, two more virtual rooms appear, while each mirror gives rise to a reflection of the original room. The combination of the two reflections lead to the third virtual room, which is a 180-degree rotation of the original room. The symmetry group of this Orbifold includes four elements: the identity, two reflections, and the rotation. This group is the dihedral group of two. When the two mirrors are placed on opposite sides, an Orbifold with infinitely many reflections appears. We can then add the third mirror, and then the fourth mirror. With four mirrors, we obtain an Orbifold with four corners. Each corner has an angle of pi over 2. Thus, the Orbifold notation of this Orbifold is star 2, 2, 2, 2. The Orbifold can be described by its Euler characteristic v minus e plus f. Here, there are four corners, and each corner occupies only 1/4 of the corner space. Thus, v is equal to 1. Similarly, e is 2 and f is 1. Thus, v minus e plus f is 0, which indicates that the Orbifold is Euclidean. Indeed, the room looks familiar given our life experiences. There are three more Euclidean Orbifolds, all triangular. This Orbifold has three corners, with angles of pi over 2, pi over 3, and pi over 6, respectively. Its Orbifold notation is thus star 2, 3, 6, and its Euler characteristic is also 0. The second triangular Orbifold is an equilateral triangle, which is star 3, 3, 3. The last triangular Orbifold is star 2, 4, 4. However, not all Orbifolds are Euclidean. In fact, most Orbifolds are non-Euclidean. A spherical Orbifold has its universal cover being the unit sphere. The edges of a spherical polygon follow great circles in the sphere, and the Euler characteristics of any spherical Orbifold is positive. A hyperbolic Orbifold had its universal cover being the upper sheet of the two-sheet hyperboloid. The edges of a hyperbolic polygon follow the geodesics in the space, which are the intersection curves of the hyperboloid and the plane passing through the vertex of the lower sheet. The Euler characteristic of any hyperbolic Orbifold is negative. We now provided an enumeration of all two-dimensional kaleidoscopic Orbifolds based on the number of walls and the order of symmetry at each corner. When there are one or two walls, the Orbifold must be spherical. On the other hand, when there are at least four walls, the Orbifold must be hyperbolic, with the only exception being star 2, 2, 2, 2, a Euclidean Orbifold. For triangular Orbifolds, there are three cases. If the least order of symmetry among all corners is at least 3, the Orbifold is hyperbolic. The only exception is star 3, 3, 3, which is Euclidean. When the least order of symmetry is 2, we consider the next least order of symmetry. If it's 2, then the Orbifold is spherical. If it's 4 or above, the Orbifold is hyperbolic. The only exception is star 2, 4, 4, which is Euclidean. Finally, if the Orbifold is star 2, 3, x, then the Orbifold is spherical if x is less than 6, Euclidean if x is 6, and hyperbolic if x is larger than 6. As can be seen in the table, there are 4 Euclidean Orbifolds, infinitely many spherical Orbifolds, but even more hyperbolic Orbifolds. This enumeration is key to the UI design and layout algorithms behind our system. Here we show our design system, with which the user can change the layout of the Orbifold, which is used as the ceiling and floor of the room. The user can put full or partial mirrors on the wall, add objects to the scene, and move or deform them. To create a layout of a spherical Orbifold, we first project the Orbifold from the sphere onto the plane using the stereographic projection. In this model, a geodesic in the plane is a circle that intersects the unit circle at a pair of antipodal points. If the Orbifold has only one wall, the room is precisely the unit disk in the plane. If it has two walls, i.e. the star KK case, they must intersect with each other at the same angle on both sides. The triangular Orbifolds of type star 2, 2K can be constructed as half of the star KK case. For other triangular spherical Orbifolds, we can start with the first vertex P1, follow a geodesic for a distance to find P2. From P2, we walk along the second geodesic for a distance to find P3. This gave us the Orbifold. To compute the layout of a hyperbolic Orbifold, we can project the Orbifold from the hyperboloid onto the Poincare disk. Inside the Poincare disk, a geodesic is a circle that intersects the unit circle at the right angle. Our layout algorithm for triangular hyperbolic Orbifolds is similar to that for triangular spherical Orbifolds. When there are 4 walls, it's difficult to directly find the length of the edges of the quadrangular Orbifold. To address this, we divide it into 2 special quads, each of which has 2 adjacent right angles. The formulas to compute the edge lengths of the special quads are given in our paper. When there are n walls where n is at least 5, we can divide it into the disjoint union of at most 2 special quads and n-4 special pentagons. Each special pentagon has 4 corners with a right angle. The formulas for the edge length of the special pentagons are given in our paper. We also refer our audience to our paper for detail on our algorithms for object embedding into non-Euclidean spaces, universal cover construction, and rendering. Our design system and mirror-based metaphor can help the user recognize non-Orbifolds, see the Orbifold itself, identify the type of the Orbifold in terms of its Orbifold notation, For example, the second corner is 5, since there are 5 pairs of the red characters approaching the corner and then leaving the corner. The same animation can also help the user identify the type of the universal cover by observing the unnatural deformation and speed as the red characters move around the scene. In conclusion, we propose a mirror-based metaphor for Orbifold visualization. We also develop a system for interactive Orbifold design and visualization. At the core of our system is the algorithm to generate the layout for arbitrary kaleidoscopic Orbifolds, embed 3D objects into non-Euclidean spaces, and construct the universal cover. We also provide an adapted rendering algorithm that takes into account the geodesics in non-Euclidean spaces. All of this is enabled by our enumeration of two-dimensional kaleidoscopic Orbifolds. In future research, we would like to extend our work to Orbifolds involving light reflections and rotations, three-dimensional Orbifolds, and non-orientable Orbifolds. We wish to thank Bo-Tong Qu for some initial discussion of this work, and Peter Oliver for the help during video production. Our anonymous reviewers have provided many suggestions that helped make our paper better. This work was partially supported by the National Science Foundation. Thank you for your attention.